Remote sensing is a process to find out about any object, place, or phenomenon without directly touching it. Usually, sensors on platforms like satellite, aircraft, drones, or ground-based devices are used to accomplish this. This sensor capture information technique for measuring an area's reflected and emitted radiation from a distance as a way to identify and monitor its physical features such as visible light, infrared, or microwave energy. Remote sensing has a long history, beginning in the 1822s and continuing to the present days. Here are some key milestones in the development of remote sensing. First, 1822, earliest remote sensing can be traced developed of photography. Second, 1840s, Milanese used newly invented cameras to take pictures of the ground. Third, 1907, there was a pigeon flight in Europe at the turn of the century. Fourth, 1942, the US Army launches a V2 rocket with a motion pictures camera on board, capturing views of the Earth's surface. Fifth, 1957, the launch of Sputnik made it possible to put film cameras on orbiting spacecraft. Lastly, 2010, our perspective on using space to view the Earth has changed as a result of Sputnik. Remote sensing is the process of gathering information about objects without making physical contact with them. It is used in many fields, including agriculture, forestry, mining, mapmaking, and disaster warning. Bathymetry, the study of underwater depth in bodies of water, is a crucial aspect of oceanography and coastal research. Accurate bathymetric mapping supports various applications, including habitat mapping, navigation, and coastal management. Traditional method of bathymetry, which often involve in-situ measurement, can be time-consuming and resource-intensive. With enhancement in remote sensing technology, satellite imagery provides an efficient alternative for bathymetric data collection over large and remote areas. It is essential for many ocean-related tasks, including oceanographic modeling, marine conservation, marine infrastructure development, and navigation safety. According to Tokino 2021.
Bathymetry classification is essential for various marine and environmental applications. It helps identify and protect key habitats like coral reefs and seagrass beds by assessing the health of aquatic ecosystems. It plays a critical role in monitoring environmental change, such as the impact of climate change on sea level rise and coastal erosion, as well as providing data for studying sediment movement and underwater landscape change. Accurate underwater maps derived from bathymetry enhance navigation and maritime safety, reducing the risk of marine accident for ship and submarine. In disaster management, bathymetric data support flood risk assessment and tsunami modeling, helping predict and mitigate coastal threat. The field also supports industry by aiding offshore energy projects such as wind farm and oil platforms and identifying sustainable fishing zones to improve fishery management. Moreover, bathymetry provides valuable insight for scientific research, contributing to a better understanding of underwater environments and enabling informed decision-making in marine policies and conservation efforts.
Based on the map provided, bathymetry classification using PLIDAS 1A satellite imagery involves mapping seafloor topography and identifying benthic ecosystem by leveraging its high spatial resolution of 0.5 meters, which allow for precise identification of small-scale features. The spectral resolution captures reflectance across multiple wavelengths, enabling differentiation of habitats such as coral reef, seagrass beds, sand plants, rocky substrate, and mixed habitats. Its radiometric resolution ensures fine distinction in light intensity are recorded, enhancing accuracy in detecting subtle underwater variation. With temporary resolution, repeated imaging facilities monitoring ecosystem change over time, making this approach a powerful tool for understanding and managing marine environment. Bathymetry classification using Sentinel-2 satellite data, as demonstrated in the study, utilizes its unique spectral, temporal, spatial, and radiometric capabilities to map the seafloor. Sentinel-2's multispectral bands, particularly in the visible and near-infrared range, effectively capture underwater reflectance for depth and habitat analysis. Its 10 until 20 meter spatial resolution enables moderate detail in coastal and shallow water areas, while the high temporal resolution of 5 days revisit times allow for consistent monitoring of dynamic marine environment. The 12 bits radiometric resolution enhance the ability to detect subtle variation in reflectance, crucial for distinguishing benthic features. Together, these attributes make Sentinel-2 a cost-effective and efficient tool for large-scale bathymetry and ecosystem classification.
And now is for the parameter. In this table, we can see the differentiation of specification between the PLIDAS and Sentinel-2. From the table, we can see the difference between spatial resolution, spectral band, radiometric resolution, temporal resolution and swath width. As the example, for the difference between spectral band is for the PLIDES, it only use 4 bands, blue, green, red, and IR. And for the Sentinel, we can see it have 13 band, 4 band at 10 meter, 6 band at 20 meter, 3 band at 60 meter. And now, for this table, it shows the difference between bathymetry depth range, application in bathymetry, data processing techniques, and the strengths of the satellite. And now is the important part of the parameter between PLIDES and Sentinel-2. In PLIDES, for the spectral band, the deep blue band allows for better penetration of light in water, which is crucial for estimating depth accurately. This band, combined with other visible bands, enhance the capability to derive bathymetric information from satellite imagery. For the high spatial resolution, the PLIDES satellite provide very high spatial resolution, up to 80 cm, which allows for detailed mapping of coastal and shallow water environment. This high resolution is essential for capturing fine scale verification in bathymetry, algorithm and data processing. The effectiveness of algorithm used to derive bathymetric data relies heavily on the quality and range of spectral bands available. The multispectral signals attenuation method, which analyze how different wavelength penetrates water, benefit from enhanced spectral capabilities of PLIDES imagery. For the Sentinel-2, for the spectral resolution, Sentinel-2 multispectral instrument provides multiple spectral bands, including blue and green wavelength, which are crucial for estimating water depth. The blue band is particularly effective for deeper water, while the green band helps in shallower areas. The combination of these bands allows for better discrimination of underwater features and accurate depth calculation. For the image quality, the quality of the satellite image, including factors such as atmospheric condition, cloud cover, and water clarity, directly impact the accuracy of bathymetric estimate. High quality image lead to lower root mean square error values in depth estimation model. For the data processing techniques, advanced data processing techniques such as machine learning algorithm and band ratio method rely heavily on high quality imagery to improve accuracy in bathymetric mapping. This method often requires calibration with ground truth data to enhance their.
The solution is satellite imagery from PLIDES and Sentinel-2 to address bathymetric challenge. PLIDES satellite provide high-resolution optical image up to 50 cm, ideal for detailed coastline mapping and shallow bathymetry. This image enable the tracking of fine-scale change in underwater features over time. Sentinel-2, with its multispectral capability across 13 bands, offer medium-resolution imaging 10 to 60 meters, making it highly effective for large-scale bathymetric observation. It can monitor sediment movement and temporal change with 4 key bands in the visible spectrum: coastal aerosol, blue, green, and red, being particularly useful for retrieving bathymetry. Temporal variation in the aquatic environment, including those caused by tectonic shift, sediment deposition, and human activities, can be tracked by collecting satellite imagery at different time points. Sentinel-2 spectral band, particularly the blue and green bands, are highly sensitive to water quality and can help identify sediment plumes and change in water clarity, indicating areas where bathymetric change may have occurred.
Two methods that we use, which is multi-beam echo sounding (MBES) and satellite-derived bathymetry. Based on combined workflow, first acquire MBES data, which map the seafloor to obtain high-resolution bathymetric measurement. Second, satellite data acquisition, which collect imagery from Sentinel-2 and PLIDES over the same areas. Third, two band that has used, which is blue band, Sentinel-2 443 nanometer and PLIDES 430 until 550 nanometer, and green bands for Sentinel-2 560 nanometer and PLIDES 500 until 620 nanometer for bathymetry extraction. Fourth, calibration and validation. Validate satellite-derived bathymetric map with MBS data to refine algorithm. And lastly, benthic ecosystem mapping, which use validate SDB output to classify ecosystem such as coral, sand, and algae.
And now is for the future research. First, it can improve bathymetric mapping. Utilizing advanced spectral bands, blue band in PLIDES can enhance the accuracy of bathymetric modes, allowing for better mapping of coastal and shallow water environment. Second is integration with machine learning. Future studies can incorporate machine learning algorithm to analyze satellite data more effectively, improving the precision of depth estimation and enabling real-time monitoring. Third is environmental monitoring. The methodologies developed can be applied to monitor change in coastal ecosystems such as coral reef and mangrove, providing valuable data for conservation effort. Fourth is disaster management. With high-resolution bathymetric data can assist in assessing risks related to natural disasters as tsunamis, flooding, and inform emergency response strategies. Fifth is marine spatial planning. The finding can support marine spatial planning initiatives by providing accurate bathymetric information that aids in habitat mapping and resource management. Last is validation of other remote sensing data. This case study can serve as a benchmark for validating data from other remote sensing platforms, enhancing the overall understanding of coastal progress.